Okay, hello everyone. Yes, my name is Joshua Lock. I'm an open source engineer at VMware, and I'm here with Marina Moore, who's a PhD student at NYU, and we are both maintainers of the TUF framework, or the update framework, I should say, and we're going to talk to you about attacks on package managers and how to defend against them. So this is the rough agenda for the next 20 minutes or so. We will probably use the term software update system, package manager, and content delivery system somewhat interchangeably. We're mostly here to talk about content repositories and the things that talk to them and the messages they send each other effectively. So I'm going to hand over to Marina now, and she's going to talk to us a bit about attacks on package managers.
Hi, thank you. So I'm going to talk a bit about a bit of history of attacks on package managers, starting in 2008 with this paper here on attacks on package managers, and going into some present attacks from the past year and how these are still relevant today. So if you go to the next slide. So let's start with today, right? These are some really recent attacks, some of them within the past month, all of them within the past year on software update and package management systems. So first of all, we have the UAE parser JS, which was an account compromise that then led to the attacker being able to upload some malicious software that was downloaded and installed by lots of folks. There was a malicious maintainer that was added to the event stream project who made a bunch of commits until they became a trusted maintainer of the project, and then they were able to push, I think this one was a Bitcoin miner, to the package. And finally, we have this dependency confusion attack, where a researcher was able to find the names of internal packages that companies were installing. And these companies were installing both from their internal repositories as well as from public repositories. And the researcher was able to convince these installers to use public packages using the names of the internal packages instead. So like they just were able to create some random packages, upload them to these public package managers, and convince people to install them because they had the same name as an internal dependency. So you go to the next slide. In general, I think there's a few different categories of attacks on software update systems that I'm going to focus on in the next couple of slides. These are wrong software installation, where you convince a user to install just some arbitrary wrong piece of software. And there are some subcategories of this, which include arbitrary software installation, most general one, wrong software installation, installing some valid piece of software, but has nothing to do with the piece of software you want to install. Maybe something else that's included on the repository or somewhere else, as well as extraneous dependency attacks, where an attacker is able to inject additional dependencies into software and convince users to install them. Go to the next slide. The next type of attack is a wrong version attack, where the attacker convinces the user to install a version other than the version they expect, but of the correct piece of software. The most common of these, of course, is a rollback attack, where the user asks for, say, the current version of a piece of software, and instead get an older version that may be vulnerable to known attacks, that may be like known CVEs about this older version. As well as freeze attacks, where the repository just doesn't let the user know when a new version of the software is available. And some kind of other attacks, including fast forward attacks, which are a response to protections for rollback attacks, where if an attacker is able to make the version number of a package very large, this could prevent future installations of the software if they're doing strong rollback protection. So go to the next slide. We have vulnerability to compromise. And this is probably one of the most common vectors of attack, which is just that the attacker is able to compromise one piece of the system, and the system isn't able to recover from this compromise. This includes key or account compromise, as we saw in the recent attack, as well as repository compromise. And the key here is the ability to recover when these things are compromised and minimize the damage when they are compromised. And we'll get a bit into that in just a second. So to the next slide. I'm going to pass it back to Joshua to talk about how we can defend against these various different types of attacks.
Thanks, Marina. So we're going to explain TUF, which is an acronym. It stands for the Update Framework, and TUF is effectively a design for securing software update systems. And TUF it provides various security properties which ensure that the freshness, consistency, and integrity of content in the repository is protected. Tuff's design reduces the impact of a compromise of repositories or keys, and it allows recovery when a compromise does happen. So how does it do these things? Effectively, Tuff describes the process for generating some signed metadata on the repository and then how a client should retrieve and query that metadata. There's a foundational pillar of trust for a typical Tuff system, which is an initial set of trusted metadata delivered out of band with the client tool that interacts with the repository, typically a package manager. And once bootstrapped, Tuff is able to protect repository content through the use of digital signatures. Digital signatures guarantee the integrity of content on the repository, protecting against arbitrary software attacks. This is actually a fairly common feature found in other secure update systems, but I think even here, Tuff provides additional benefits compared to those designs because it has built-in kind of key distribution and replacement features. We also use digital signatures to guarantee the consistency of the repository itself, which protects against the mix and match attacks that were described briefly earlier. And Tuff uses expiration times on signatures to do things like ensuring the freshness, because once a signature is expired, content is no longer valid. So we can indicate freshness by having the repository operation, when it proceeds as expected, periodically regenerate metadata with a new signature, and this acts something like a heartbeat signal indicating that the repository is alive and well. When a key compromise does happen, the impact of that is reduced through the use of roles and threshold signing in Tuff. So each of the integrity, consistency, and freshness guarantees that Tuff provides are enabled by separate roles within the system, and each role has separate keys in use. Tuff has a mechanism for threshold signing, which allows multiple signatures to be required for each role. So, for example, if you have a repository with multiple operators, in order to authorize changes to the super user-like root role of the repository, you could require that 3 or more of those operators sign the changes. And then Tuff's design enables effectively minimal risk to be placed in keys minimal trust to be placed in a key that is at high risk. For various deployment scenarios, you might have a key that is online and used in some kind of automated fashion, such as the timestamp key, which provides the heartbeat we previously discussed. And a compromise of these higher risk keys with lower trust does not pose an immediate risk to the clients due to the separation of duties in play here. For higher trust roles, we recommend the use of offline keys and the use of thresholds to increase the cost of a compromise. And should a compromise happen, Tuff has built-in mechanisms for recovery. The super user-like root role delegates trust in a tree to other roles in the system and to itself. And the keys for any of these top-level roles can be updated by modifying the root role and having a threshold of signatories signed for those modifications. So long as a threshold of the root keys are not compromised, any key in the system can be removed and replaced through updates to the repository metadata. So in summary, like why adopt Tuff? It provides content protection for the contents of your repository. It enables repository operators to independently provide some trust for their repository and delegate aspects of that trust to appropriate others. For example, allowing package maintainers to sign their own packages. And of course, this is a nice thing because if the package maintainers sign packages, it prevents an attacker who manages to compromise a repository from tampering with those packages because the key is effectively offline in the developer's possession. And Tuff reduces the impact of a compromise and allows recovery when should that happen, which, given the increasing attacks on nodes in the supply chain, seems like a goal we should all be striving for right now. So perhaps this brief introduction to Tuff has intrigued you. Many would be inclined to think this is a major change, but one of the key tenets that Tuff was designed with was to be supplementary. It's intended to augment existing systems without requiring invasive changes. There are many open source implementations of the formats and workflows within the Tuff specification. So if you're using Python or Go or Rust or PHP, open source implementations of the framework exist. And just as an indicator of how much effort it actually is to integrate one of these frameworks into a package management system, a colleague and co-maintainer of the Python implementation of Tough, UC, recently did a proof of concept integration into the pip package manager, and the diff stat was 633 lines added, 47 removed, which I think is actually quite an impressively small change for the amount of functionality that is integrated. So after that whistle-stop tour of Tough, I'm going to hand back to Marina to describe some of the ways Tough may have helped with the attack disposal.
Yeah, so really a quick game of would Tough have helped protect against various recent attacks on package managers. So the first one is dependency confusion attacks. This is the one I mentioned earlier, where a private company or whatever is using two different repositories, an internal private one and a public one, and they're accidentally pulling malicious packages from this public repository. And the way that Tough protects against this attack is through two different mechanisms. So first we have the separation of responsibilities, which Joshua talked about. And specifically, this means that the namespace delegations in Tough ensure that the key that's signing the package is specifically the user that is trusted to sign for that particular package. These are really like specific delegations that say, this user is trusted for this package, but not for like all of these other packages that may be on the system. And this means that using these specific delegations, the system can know, okay, this was the actual correct user that signed for this package, and not some random user on the internet that maybe shouldn't be signing this particular package. And the second way that Tough can be used to protect against dependency confusion attacks is using mapping metadata, which is described in an augmentation to Tough called TAP4 that basically extends this property of delegations to multiple different repositories instead of just multiple different users on these repositories. This is described in way more detail in the documentation, but essentially it allows you to say these particular packages should come from our internal repository, and these other packages can come from instead from this external repository. So you have an expectation of where these things will come from, which would prevent this attack. And next we have the UEA.js parser attack. And again, Tough will protect against this in a couple of different ways. First of all, Tough does require all packages to be signed with trusted signing keys. So especially if a developer maintains offline signing keys that aren't stored in the same place as their account, so, an attacker who took over the account would not be able to upload valid packages because they wouldn't have access to the developer's signing keys. And so this just kind of separates that piece and makes it a little bit harder to take over. And secondly, even if the developer, for some reason, decides to store their signing keys as part of their account, Tough allows for easy revocation of these keys. So someone higher up in the delegation chain, top level targets, or the repository maintainer can revoke the keys for the developer as soon as it's clear that an attacker has taken over the account. So the developer can then notify the repository and revoke access to these keys to prevent anyone in the future from downloading the malicious package. So that's how it would prevent this attack as well. So now I'm going to pass back to Joshua to talk a bit about who's using Tough today and kind of models for how Tough can be used.
Thank you. So yeah, we actually have many deployed Tough systems today. You can see I've tried to group them into various categories here. So we have a bunch of adoptions, which are people who've implemented the Tough spec as written and are using it in production systems today. You can see some interesting examples in here, including Datadog used Tough to protect their agent updates, and AWS BottleRocket OS and Google's Fuchsia OS are both using Tough as the fundamental security for their operating system package managers. We have several work in progress adoptions happening kind of right now, including the Python package index is working to integrate Tough. And both the Drupal and Typo3 communities are collaborating on a PHP implementation of the Tough client and looking to integrate those into their systems for secure updates of the core content management systems and for extension installation. We have a a very interesting derivative of Tough in the Optane project, which is an automotive-focused variant of Tough. And one of the fundamental premises for Optane is that whilst a typical package manager will query a repository for available updates, in the automotive case, it's nice to be able to push updates to the clients. There's also various other considerations like frequency of connection and the power of the computing devices in an automotive system. And so Optane takes the core Tough framework and extends it for this use case, and is actually seeing some additional use in IoT, which has a bunch of similar problems, similar concerns. And we also have various adaptations of Tough, and these are systems which have looked at Tough, seen some things they liked in it, but recognized that maybe some of the properties of Tough are not applicable in their scenario, and so they've effectively adapted Tough to their different package management systems. And we see that with Conda recently announced their Tough-based repository trust solution, and the Geeks and OPAM communities have been running a slightly modified version of Tough for quite a while. So yeah, I think there's a lot of interesting applications of Tough to different scenarios, which demonstrate the system's adaptability. And that's something we try to encourage upstream, very open to discussions of how you might adapt Tough to different systems. Which brings me on to the next section of the talk, which is effectively how do you learn more? So if you are interested in Tough, we are very interested in helping to protect the packaging ecosystem, and we're very open to discussion about how we could make Tough adoption more compelling or easier for package ecosystems out there. So we have a Google Groups mailing list and a Slack channel on Cloud Native Slack, which we're more than happy to engage in discussion through. We also have a website that describes the framework and links to our detailed specification. And with that, I'd just like to thank you for your attention, and thanks to all of the Tough contributors who have contributed to this talk and the project. So thank you. And if you do have any questions, we'd be happy to take them.
Yeah. Thank you. We do have a couple of questions from the element.io chat, so I'm going to post them now. The first one is, does Tough protect against the maintainers of the registries themselves getting compromised?
Go ahead, Marina.
Yeah, I'd say that more than protecting against them getting compromised, it provides means for recovery if they are compromised. So it allows for, there's multiple different roles that some of which require a threshold of keys to sign. So if only a single maintainer is compromised, obviously this wouldn't lead to a compromise of the repository or registry. But and it also allows for recovery. I think that's the biggest thing there.
The next question is, in your experience, how difficult is it to integrate Tough into existing packaging systems?
That's a great question. So I think it's the difficulty is often the human processes that come with it. And so for single applications or applications or deployments with a strong kind of ownership model, for example, the Datadog case or the AWS BottleRocket OS case where there's an organization in charge, it's relatively easy. But some of the human processes, when we start looking at like volunteer maintained and self-service or open submission content repositories, gets a lot more complicated. So that's a lot of the complexity in the PyPI case is not so much in the software side of integrating Tough and figuring out how to have pip utilize Tough, as already demonstrated. It's a relatively small amount of code to do that, but the human processes of ensuring that the key signing ceremony is operated in a way that meaningfully provides trust, and figuring out how to do those delegations without requiring one of these repository operators, volunteer repository operators, to do a bunch of offline signing. That's where most of the difficulty, I think, has been in some of the more complex adoptions. Marina, do you have anything to add? I know you've been looking at different kind of use cases to what I have.
I think it depends a little bit. Yeah, exactly on the particular use cases. I think that especially for integrations that are similar to existing ones, there's a lot of work that's already been done that you can kind of take advantage of. So.
Okay. Let's see. I think we have time for maybe one or two more questions. This one's pretty good. Does Tuf map its namespaces and its namespace allocation with the namespaces of sort of the underlying tools, which I assume means the upstream projects?
Yeah, I think it can. Again, this depends a little bit on how the integration is done. And I think wherever possible during these integrations, we like taking advantage of existing pieces of the system. Like, for example, the Tuf snapshot file is often very similar to an index that most repositories already maintain. And so we can take advantage of these existing pieces to make that easier.
Yeah. And I think for the last one, does a repository need so many keys and roles? What if we just store what if we store the online root key in a key management system and just use a single offline root?
Yeah, I think the security properties that you get can be better with multiple offline keys, especially for the root role. And I think that this is kind of where it breaks down, right? There's a lot of different roles in Tuf, and some of them, like the timestamp and snapshot roles, you can pretty easily achieve the security with a single online key for both of those roles that you can easily revoke. But for the root role, for example, you really do want multiple independent offline keys, because this is how you recover if anything else is compromised. So it depends on your threat model, how much security you really need from it. But I think there is an importance for having thresholds for at least certain roles. I don't know if Joshua, if you have anything else to add there.
Fully agree with that. There's been a few adoptions that have suggested merging, for example, snapshot and timestamp into one online key. But certainly for the root role, and depending on the type of deployment, the target role, using multiple offline keys is much more secure for the compromise resilience property as much as anything. And it's actually one thing that we'd like to improve is our kind of documentation. So it'd be nice if we had some more of these different applications like mapped out as a playbook almost. It's on the list. We just haven't got around to it yet. And most open source projects.
Yep. All right. Well, thank you very much, Joshua and Marina. And we'll start moving to the next session. Thank you.
Great. Thanks.